Please observe. Go ahead, spend about the next 2 minutes. Just observe this for me and see what you pick up anything. Just smile and observe. Go ahead. What? Don't questions yet. Just look. Oh, family. That's the square. Okay. Okay, so who has an idea of what you're actually looking at? Isaiah, go ahead.
Radical populism.
Well, yeah, of course, but well, at least you know what it means. Radical, fine. But I'm talking like overall. What are you really seeing? Starting with the very first line. What am I really doing, Jennifer? This overall fine. You want to give me an overall take on this? Fine. As an overall, I really want you to see the whole thing as what? Yes.
It looks like they're going like, if you put it like backwards and then did the opposite operation.
Oh, interesting. You said something about opposite what?
Family property.
Operation.
Opposite operation. And it is. You're right. And he's correct on that, which is great. Notice that, why are we doing opposite operation, by the way? You know why? Why do I have to do it? Well, let's take a look. Look at the first line. I start with a 1. I add 2, I get a 3. That's simple enough, right? And then on this side, I take the answer from the other side. I take away 2 and I get back a 1. So what does that demonstrate? First of all, it's opposite operation, but what am I getting back though? What was it? What am I actually getting back over here on this side? The same number as what? As the first one. So basically, aren't you just basically undoing everything that you've done?
Yes.
Right? You start with a 1, I did something to it. Well, okay, in this case, I add something. But if I want to go and undo everything, I have to perform what Nicholas just said right there. Opposite operation. Yes? Yeah, go ahead. Opposite operations, and I get back to, it's what we call the original state. So can't you agree that your subtraction here is like the anti-addition kind of deal. It's just the exact opposite. It's undoing everything that addition does to a number. And look at the same thing for line 2. What am I doing? I take 5 times 4, I get 20, right? And then of course I say, I'm not happy with 20. I just want to go back to the original state. Just like how you have your undo button on your computer, because I'm not happy with my screen background. I just want to undo it. You can certainly do that on computer. And this is like the very basic foundation of how the computer really works. To undo something you perform, we call the opposite operations, right? And so to undo the multiplication, we do what to it? Dividing. So there it is. I take the current result. I don't like that current result, so I just undo it by dividing. Of course, I still have to use some terms that I had before. And there it is, 20 divided by 4, and I get back its original state. Okay, so those were the operations we learned from before. But look at this here. We talk about exponents before, power. We know what 2 squared is. I kind of gave you that quick demonstration. 2 squared is 2 times 2. Is there anyone here who doesn't know how to expand your power? For example, 5 to the 3rd power, what does it mean?
5 3 times.
5 3 times. Meaning 5 times 5, or what is it? 5 times 5 times 5. 3 times like that. And so I have 2 squared, 4 squared, 7 squared, and you're probably asking, why is it I'm dealing with just square only in this case? Because if you look on this side, and some of you have talked about this already, what is this symbol?
Square root.
Ooh, okay, so I heard square root, and what else? Radical. Right. In general term, that symbol right there is called radical sign, right? But because we are dealing with the power of 2, that specific radical sign is called square root. And do you know what that number inside that radical sign is called?
4.
I just want a name for it. You know that?
A square?
No. Here we go. Listen carefully. We call this well, of course, the outside is called the radical, and inside we call it the radicand. Radicand, okay? All right, so the radicand lives inside this house, and we call this house the radical. Okay? But if you notice here that the radical, in this case the square root, is like the anti-squaring, isn't it? It's kind of undo everything that the square does to a number. For example, I start with a base of 2. I square it, I get a 4. I don't like the 4. I want to go back to the original state. Guess what? How do I undo it? Square root it. So undoing. So now you know that addition has an anti-operation to it. We call that subtraction. The multiplication has its opposite. We call that division. Power of 2, or square, we have the exact opposite of it. We call that the what? Well, it's more specific to the power of 2. What is that called? Square rooted, right. So there it is. And we're definitely going to dig deep into this to see what's going on. But at least you see something here that we kind of know the very basic of, and Jennifer earlier mentioned that these are what numbers, Jennifer? Perfect square. And that's why when we take this square root of 4, we get it back to 2. We get the square root of 16, we get it back to 4. We take the square root of 29, we get it back to 7. But do you know where that 7 actually came from? Do you have any idea on that? Where do you think I get the 2 from the 4? Where do you think I get the 4 from the 16? Where do you think I get the 7 from the 49? Where is that coming from?
Squared.
Okay, so you talk about a number multiplied by itself, right? Okay, good, good. So I want you to hold that thought. I mean, we're not getting to the concept yet, so at least I want you to understand about, oh yeah, something number by multiplied by itself. So here's our question for this prompt. I asked, what about this? That's square root of 48, and all of a sudden, like, wait a minute. Square root of 48, is that a perfect square number?
No.
No, so can we actually take the square root of 48? In the past, in 7th grade, of course, back last year, we got estimated, right? Okay, but now we want to get to very specific. We want to be able to, we call, simplifying. Oh, by the way, we talked about simplifying before. Simplify means what?
Make it easy.
Oh, we know we make it easy, but in terms of making it easy, what do we really do?
Break it down.
Break it down. Ooh, I love that. Breaking it down. So here it is. Here's the first concept I want to talk to you about today. We call it, you want to leave the house? You have to pair up, please.
Oh. Oh.
Oh.
Like the twins thing.
Oh, the twins. Okay, good. I love that.
Oh. And then one dies, and then, sorry.
Okay, good.
Yeah.
Good. That kind of reminds you of something, which is great, right? But here it is. So I want to start with this very basic problem that we started with. Take a look. We have the square root of 16. We know what the answer is, right? It's 4. That's easy. But let's actually break it down and see how 4 came about. So let's take a look at 16. Remember I asked you about simplifications, and then Centennial talked about breaking it down. So okay, fine. But think about this. Let's break down 16. Can someone help me break down 16?
4 times 4.
Okay, 4 times 4. Can we still break it down?
2 times 2 times 2.
Okay, so that means 2 times 2, that's what I got for 4, and another 2 times 2, right? Okay, so I want to tell you a little story before we start. Think about this. If your parents gave birth to twins, I'm talking about identical twins, inside the house, I'm pretty sure your parents would know that you are Jennifer, the other one would be Jenny, for example. Is that true? Because your parents would know who's who. But if you were to go outside of your home to 2 different places, you think people will tell you apart? Ever?
No.
No. So technically speaking, even though you are represented as a twin in your home, your parents know both of you exist. But out in the outside world where people don't know you, only one actually exists. Is that true? Because since you look identical, if you met 2 different set of people and asked, okay, can you just draw Jenny? Let's just draw one exact replica for the both of you. So I want you to use that twin concept to do this kind of work. So look, think about this. Think of your radical sign, or square root sign in here, as your house. Inside the house, you are 2 separate individual. Parents know who you are. But, when I talked about you have to pair up when you leave the house, but as soon as you leave that house, how many representation of you people would know about? Only one. Is that true? So that means, mathematically speaking, if we're going to have to go relate back to radical, when you actually take that twins outside of the home, there is only one representation of that twin. Because anywhere you go and ask, hey, can you draw Jenny or Jennifer? They'll just draw exactly one copy. Is that true? So there it is. So we see that twin, we take it outside the home. There's exactly one copy of it. Okay, do we see another twins in here?
Yes.
There it is. Is that true? And guess what we'll do to that twin?
Only one copy.
Yeah, exactly one copy again. We take that twins outside as well. And what do we do when we have twins outside? Well, in this case, mathematically, they multiply. And there it is. So what's 2 times 2? 4. And what's left inside the house? Nothing. So nothing, we just go ahead and that house is abandoned and we're done. So no more house here, and that's our answer. 4. And that's how we got square root of 16 to be 4. So you see this basic concept? The basic concept of twins, how when you actually take that outside the home, there's only one representation of that twin, because that's how I receive anyway. And luckily enough, I mean, in my first period class, I have Jordy sitting right there. I'm like, oh yeah, you reminded me of your brother, but I can't really tell you apart. That's why I'm saying, yeah, you're a perfect example for this lesson. You know? Okay, there it is. So if you understand this part, take a look at this one. Go and try it yourself. Take the square root of 75. Oh, yeah, good. And once you're done with that, I want you to go back and answer this question for me. Remember we start with this, square root of 48? So we'll go ahead and do both first. So do 75 first. So you can actually break any twins out of the house for that one. Yes? Did you do 48 as well? Oh, wow, okay. Fair enough.
Cheater.
No, she's not cheating. She's just working fast. Remember, the concept is simplifying. Simplify means break it down, right? See? So I give you that buzzword. Yes. See that? Can you break down 75?
Yeah.
Go ahead. Okay, well, break it down all the way.
Only get all of that.
Well, break it down. Seek out the twins. You are put on your goggles and seek out the twins.
I don't remember. Oh, Mr. Webb.
Yes. Okay, can you, what do you have here as factor form? Can you put it all underneath your house? And then now you can seek out the twins. Well, go ahead, right now. Did you break, remember every time you have your prime factor, you would circle it, right? Is that true? So these three would be under the home, right? So go ahead. Come on, let's get started.
What is it, right?
Okay, so I see a lot of people actually breaking it down, which is great. Okay, that's of course is your first step. Right, and what do you have left inside the home? Remember, the loner has to stay in the home because, you know, you're not a happy person, you stay in the home, right? Only happy people to leave. Okay. Okay. Alright. Alright, bring you back up here. Can anyone tell me, if you break down 75, what do you have? 5 times 5 times 3. Now, okay, wait a minute. Put on your twin seeker or twin goggles, whatever, to help you identify. Do you see any twins here? 5 and 5. Look, I circled that twins. I said, oh, you're happy. You're happy. Let's go ahead and leave the house, please. You're all like done grown in my house. Leave. All right. Take it out. If these twins leave the house,
Just 3.
what's left over inside the house? Just the 3. And what's outside the house now? And one representation of it or 2? Just 1. Remember, twins, I only perceive you as 1.
Okay.
That's what's happening. So be careful. Now go ahead, repeat that to 48, please. See what you have.
That's okay.
Got it?
Wait.
Well, we can break it down. 4. Have 1, 2, 3, 4.
24 times
You only bring the twins outside, not the loner. Okay. So
Oh, you bring that.
loner stays inside the home. Yes. Okay, don't forget, only the happy pair will leave the house.
That doesn't seem
Not
fun.
alone. How many pairs did you bring out? Another 2 right here, right? Yes.
Oh, wait a
Which
sec.
one? What are you bringing out? Did you break it all the way down? I didn't. That's my question. It's for completely simplified. See that?
You mean like the ones in this one?
Yes.
The one with all the baby.
Okay, how many parents did you bring outside? Which is actually good. I mean, I'm glad I gave you this problem as a prompt because of this. 48. You break down 48, what do you got?
3 times 2 times
3 times 2 times 2 times 2.
How many twos, basically? Four. So you have this, right?
Yeah.
You see our twins here?
Yeah.
How many pairs of twins?
Two.
Two of them. So the first pair that you take out, there will be one representation of it outside. Okay, now this is what people miss. You forgot there's another twins in the house that need to leave. You know, there's only the house big enough for loners, not twins. So move out, please. So there it is. I take that twins and take that out of the house as well. That means I have another what out here? Two. And what do you do with that? You multiply them up. Whatever you take outside, you multiply them all together. Okay? And what do you have left now? The 3. And so, 4 outside and 3 inside. Okay? You see the idea? Okay. So break it all the way down, seek for the twins, bring it outside. One representation of twins. I don't care how many pairs you take outside, they all multiply. Because they're happy outside. Okay? Moving on. So, what is this next concept going to be? I don't know. Oh, there it is. Keeping the positive alive? Oh, okay, I get it. Oh. You kick the twins outside of home, right?
Yeah.
But don't you want them to be happy? Because you don't want them to move back. Keep them happy outside. That's the whole concept. Usually when you're 18 and older, your parents say, just leave, you know. They don't want you to come back. And so they want to make sure that you are happy outside.
I want to be.
Okay, so how do we do this math, right? Oh, let's take care of this. Think about this for a moment. I'm going to give you a very basic example. Here it is. Let's say I have x squared and I want to take the square root of that. Okay, now what do you see about x squared? How many x's do you have? Okay, remember we break it down first. So that means we have x times x, correct?
Yes.
Okay. Do we see our twins?
Yes.
What? S. So we take that where? Outside. Do we have any left inside the house?
No.
No. So, over here though, of course, you now agree that the square root of x squared is x. Is that correct? Pretty easy concept, right? And you say, okay, so what's wrong with that one? There's nothing wrong. Not until I give you something like this. Pretend, what if x here is a negative 2? You're saying, okay, well, so what? I plug it in, I'll prove it. It's going to work. The left-hand side will equal to the right-hand side. Let's test it. If the x is negative 2, that means I have negative 2 squared, correct?
Yeah.
And we know very well what negative 2 squared is. Positive 4? Oh, we forgot about that concept. A negative times a negative is a positive. So it's the square root of 4. And yet over here still, we have this as negative 2 because we declare that x is negative 2 to begin with. What will happen when we take the square root of 4? You get what? A 2. Wait, is that a negative 2 I'm hearing about? No, it's a positive 2. And all of a sudden, is this true? No. So how do we write this? In other words, if we're going to kick this twins out, we want to make sure that that lonely twins outside now need to keep his or her composure and be happy. And the way to make it happy is be positive. And in mathematics, how do we make it positive, you know? Not times. If I say we don't allow multiplication in this case. What? No division either. No operation at all. What do you think will make this negative 2 positive? Let's see if you have to remember that. Anyone?
Add it to the other.
No adding either. It has to stay as is.
Just make it positive.
So
That's it. No operation, no other operations allowed. Do you still remember what is it that we can make? What thing? Oh, wait, say it.
Oh, the absolute value.
Absolute value. The absolute value will make it positive all the time. Touchdown. There it is. So, here's the thing that we need to learn today, or this in this case, that if you're going to kick the twins outside the home and it's going to be lonely outside, you better make it happy. And how do we make it happy? We absolutize it, or I'm sorry, not even words, but sure, absolute values around it. Okay? And that's how we do it. Every time we bring a pair outside, it's gonna be a lonely pair outside. I'm talking like the odds one. Make sure you make it happy by putting absolute value sign. Okay? Any questions so far on that concept? Okay, good. Now, let's see if you can actually experiment with this one. So now I have both numbers and variables involved. We know how to take care of our numbers. Let's try this. If you break down 50, what do you have?
10 times 5.
Bring it all the way down, please.
2 times 5 times 5.
5 times 5 times 2. Always check again, make sure that if I multiply these three numbers up, I'm going to get back a 50. Indeed, I do. What about the n cubed? How do I break that down?
M times M times
Okay, perfect. What about the n fifth?
N times
N
N
times
times
N
N
times N times N times.
Okay, so 5 n's like that. All right, put on your twins, tweet, seekers, goggle, whatever you want to call it, and seek out the twins. Do we see any twins here?
5.
Okay, let's just do it one at a time. Here's a 5. What else?
M.
Okay.
N.
No, there's 2 N's.
Oh, okay, so there are 2 pairs of n's in there. Okay, all right, let's take it outside. Kick it out. Go. What do we have left outside here? 5 m.
N. Squared.
Oh, because we have n and another n, right?
Yeah.
And so that's n squared. Very good. I mean, we brought outside 2 pairs of n's, and there we have it. Okay, what's left inside? 2mn left over. But then again, remember I told you that we need to keep certain people happy? What needs to be happy outside? Which variable? By the way, we only care about the variables.
The N.
The m or the n?
N.
Wait, let's just say carefully. M, n, oh, the n.
That's a mark. Yes.
M is like your
Oh, we
mama?
just go.
Or-
Yeah, we just go.
Okay, which one is lonely?
M's by itself.
Good, there you go.
So why don't we just do
Why not the n?
Oh.
It's squaredy. It's, it has a pair. It's happy. They're happy. We don't need to put, our absolute values around it. We're done.
Mama needs to be happy.
Okay, but do you see the concept behind putting the absolute values for twins that being taken outside? If they're not happy outside, meaning odds ones, in this case, loner, odds, powers kind of deal, you want to keep it positive. Okay? Question on that basic concept? Okay. Woo. Lots of,
Mr. Newman, you seem excited about this.
I love this. I know, right?
Easy.
Oh, wait. Oh, wow.
Kill it.
Divide and conquer?
Uh-oh.
What is this?
It's
Divide
not
and
a-
conquer. What am I talking all of a sudden, right?
You have a leader, you divide and conquer.
Okay. So how's this going to play into our lessons for this particular concept? Think about this. If I give you a problem such as this, we all know what to do, I hope. I have 2a times it by 3a. What do you do?
6A squared.
How do you do that?
Distribute.
Exactly. Tell me what you do. Go.
Distribute.
No. Just tell me your step. What do you do? Oh, wait. Say it again.
3 times 2.
Oh, 3 times 2. Oh, why not 3 times a? Oh, wait. Why not 2 times a first?
Because it
Huh?
already has an A.
Huh? And what am I saying? Why?
Because then that wouldn't have done anything.
Oh, really?
Yes.
What's another way to say it? This 2 is a what type?
The real number.
It's a number, and the a is what?
The variable.
And we have a number, variable, can we mix them like that? This is what I'm talking about, divide and conquer. So, what I mean is, when you see your number and the other number, let's just go ahead and put them together first. That's why people would say, oh yeah, I always take 2 times 3 first. And then the leftover, a and a, right? We pair them up. But of course, we need to divide them up first. Okay, so what is 2 times 3? 6. And there's a trick question. What is a times a?
A squared.
Ah, I thought you were going to say a. A squared it is, right? Okay,
So wait. A plus A is 2A.
very good,
Okay.
yeah.
So
'Cause, like,
it's an
here. 1 notebook plus 1 notebook is 2 notebooks. You don't have 2 notebook squares, right?
Yeah.
Okay, alright, so, now that we understand this very basic of divide and conquer technique, take a look at this one right here. Do you see anything that we need to kind of break apart?
Yes.
Okay, let's think about this.
Sorry.
Hey, lady, listen, look over here. We have 7 root 30 times 2 root 6. Square root 6.
Yeah.
What do you suggest I should do?
Just start
Break
dividing.
it up.
We have division here?
Yes.
Break it up into 30.
Before we even break it up. Oh, what do we mean break up to 30?
Multiply.
Wait. You say multiplying what? What do we multiply?
7 and 2.
What do we say again? Out loud? 7 times 2. Why? Oh, why? What do you mean? What makes them the same? They're both outside. Very good. See, kind of like the last problem. I have numbers and variables, numbers with numbers, variables with variables. Here, I have people who live in the house and people who live outside the house. Outside, hang out with people outside, right? Inside people, hang out with people inside the house. And that's why we pair them up this way. But of course, what's linking them? Multiplication, and we still have to multiply. So let's start with that. What is 7 times 2?
14.
Okay, that's easy enough. But here's a trick one.
180.
Okay, the whole concept, wait, the whole concept is called what? What is it, what we're trying to do?
Divide and conquer.
No. Okay, yes, divide and conquer, but what are we trying to do every single time? What's the start of this lesson? We are trying to simplify. Simplify, in this case, you multiply to make it bigger. Are you simplifying things?
No.
No. So if we're trying to simplify, instead of multiplying 30 times 6 to make it 180, what is a better way to do it? Say it again. Break down to 30. Oh, great. So let's break down to 30. We know we have to take 30 times 6, right? If we break down to 30, what do we have?
6
And of course, we know we have to multiply by 6 too. See it? People inside the house stays inside the house. But notice, I did not multiply them to get a bigger value. Instead, I break them down, and guess what I just found here? You see anything? Twins! Woo! There it is. Here's the twins. What do we do with that twins? Take it out. So we take it out, what's left over inside the house?
5.
Okay, so what do we do with that twins outside the home? Which is?
84.
There it is.
Yay.
Okay. Remember, every time you do this kind of problem, always remind yourself that I'm trying to simplify here. I don't want to make things bigger for me. We do. Okay? So, question on this? Alright. Now I want to use the same technique and try to divide and conquer this one.
Uh-oh.
Can we actually divide and conquer this one?
Just got real.
What's your suggestions on this? What should we do?
Separately.
Focus on one number.
Very good. Focus on one, in this case, one level at a time. And here's this, here's something you should do. We have fraction inside this radical sign, right? And Jennifer just mentioned, hey, we should just focus on one number at a time. In this case, each number is at each different level. So that means I can actually break them apart. Since they're both living under the same roof, I can still have them separated and still live under the same roof. This is like the upper story, this is the lower story of your home. Kind of like that. But notice, once I break them apart, this makes it a lot easier for me to worry about each case, rather than the whole thing as one fraction. Remember how much, I know how much you need fractions, and this is the one way to kind of remedy this, to make it easier for you to see. And so, let's take care of the top story. Can we do anything with the top story?
3 times 3.
What is it?
3 times 3 times
3 times 3 times 3, okay. Any pair? Twins?
3.
3. So what's left in there?
3.
Okay, we got that. What about the p squared?
3 times p.
Okay, so we got p times p. Alright, let's start taking things outside here. You said that there's a twins right there, so we have a twins at the bottom.
Yes.
So what do we take outside for the top?
3.
3. What's left inside?
3.
3. Look at the bottom.
3. Wait,
What do we take outside? P. Is it happy outside?
no, you have to put the thing in Bobby.
Is it happy? How do you know it's not happy?
Because it's slow.
It's lonely, or not just by itself sometimes. Sometimes we see like,
Because Papa ain't happy.
okay, fine. Alright, you take that. Remember, understand something. Yeah, lonely would definitely be sad, but sometimes you have like odd. Talk like, look at this. Imagine they'll have a PQ. Is that paired correctly? Is someone's going to be sad about this? Yeah. If that's the case, you still need to put the absolute value to make the whole thing happy. Okay, so don't forget about that. So we are focusing on odd powers outside. We want to make the odd power happy. So be very careful. Okay. All right. Got that? Okay. Now here's the thing. Can you rationalize it now?
What do you mean
What am I saying, right? Like, please rationalize me. Oh wait, you know the whole point of this is this. From the start to finish, we talk about radical, right? You know how radical is always people who's like over the top kind of deal? Like, you're radical, you're good, so you're like up top. Is that correct?
Yeah.
So it'll be so weird for us. It'll be so weird for us to see radical in the denominator talk about the bottom level. So when we talk about this, the way that we make people radical again is moving it back to the top. So think about this. I have a case for you. Imagine I have this. Let's say that. What's not so radical about this? The bottom. Remember I told you radical, I really want that radical person to be up top, not down below. So every time you see radical right there in the bottom, you say, it's like begging you, please radicalize me so I can be radical again. You know, because it's like having a zero underneath your fraction, because it'll be undefined. It's kind of like that. We never like to have radical in the bottom at all. So the question now is there a way for us to move it back to the top? And you say, yeah, just move it back to the top. But that will change the whole problem, right?
Multiply both the top and the bottom by that same number.
Oh, not just same denominator. Let me show you. And listen, look at this. The way that we do this is really, really simple. And you're going to be happy that you learned this technique today. All we have to do is just focus on what needs to be moved. That radical. Radical 3. I don't care about the 3. It's already outside. It's not radical. It can stay down there if you want. But once we identify the radical, and just like what Jennifer said, instead of multiplying the whole denominator by itself, we simply multiply top and bottom by the same radical, which is just square root 3. But you're asking, wait, wouldn't you be changing the problem, Mr. Nguyen? Not really. What is root 3 divided by root 3? 1. Anything times 1 is itself, so I'm not really changing anything. I'm just making sure that I can get rid of this radical in the bottom. So, let's help me multiply this here. What is 2 times root 3? 6. Oh wait, are we allowed to have people outside multiply it inside? No. So what is it going to be?
2. Yeah.
2 what?
2 radical 3.
2 radical 3. Very good. Always think, if there's nothing here, there's like a 1 right there in front. So it's technically 2 times 1. Okay? And down here, let's look carefully. What's that out here? We don't see it. 1. So technically it's 3 times 1 is 3. And here, what is root 3 times root 3? What is root 3 times root 3?
30.
Okay. No, just start slow. What's root 3 times root 3? Radical 9, right? Okay. And let's see if we can actually clean up somewhat. Hey, wait, radical 9? What is that? What is this number called?
Radican.
Wait, no, radican, but what is 9 specifically? What is it? Perfect square. Perfect square means we can always find a perfect twins in there, isn't it? What's the perfect twins here for 9? 3. Right? So that means what can we take outside?
3.
The 3. So watch what happened. We have this. We take the 3 outside of the house. That means there's nothing left. So we have 3 times 3, right? Because there's a 3 outside of this already. So what we have here? 2 radical 3 over 9. And that's how we rationalize. Okay? Rationalize simply means I need to make you radical again, moving you to the top, because you are rad. Very good. Oh, there it is. Okay. Hey, try this one, please. And we'll talk about the DMQ. Go ahead. See if you can actually do that. Remember, we can use the divide and conquer technique on this. Go ahead, try to do that. You don't have to look at it as a fraction. Be right there. Can you break it apart? Top level, right?
How do you break apart a fraction?
Remember?
Shoot it.
Got it.
Are you multiplying that? Okay, so yeah, you certainly do that.
Wait, no.
What is 7 times 2?
14.
No, I'm turning down.
It is a 1.
Okay.
We need
Did you rationalize? That means we cannot have the radical at the bottom, right?
Yeah, go ahead.
There's only one.
Yeah, there's one of them.
Can you rationalize it?
No.
Why not?
How do you break apart a fraction, Mr. Ray?
What's the technique to rationalize again? What are you doing? The bottom. Alright. Itself, basically. Okay, can you do that? How do I rationalize that? Not bad. Oh, nice. Oh, I good that you actually caught that. Nice. Okay, I'm seeing a lot of people multiplying across, which is not that it's wrong. You're just making it hard for yourself. Okay.
You cross that.
Okay, look. And you're right in a sense that you break it apart, right? Or for those who can recognize it, or you don't have to write it, just to save time, but you can certainly just multiply across. People who did this to get square root of 14 over 321, you're on the right track. You're only one step away from getting it done by getting rid of this. How do we get rid of this? By? Okay, radical 21. This bottom and top. Okay, now here's the thing. That's get complicated, right? You know. But we can certainly break it down. You forgot one thing though. You can certainly pursue this approach and still get the same answer, or looking back to here. Do you see anything that can actually cross cancel?
Oh, I thought we couldn't do that.
They're linked by what? Multiplication. Every time there's something linked by multiplication, we know we can cross cancel or whatever. Okay? So if you do that, you end up with just root 2 over root 3. And now it makes it a lot easier for us to rationalize. How do we rationalize? What do we multiply this thing by?
Radical 3.
And root 3, right? So let's multiply. What is that going to become on the top? Root 6. And the bottom? Just 3. I hope you catch this on, because 3 times 3 is 9, and square root of 9 is 3. So always, when you have a root multiplied by itself, you always get back the number inside the house itself. Just like how I talked to you about the concept of undoing things, that's what's happening. And here it is.
3 the absolute 3.
I got the answer.
Oh no, that's just the.
Okay. Okay. We're good? Alright, here's your, I don't have another problem, but we're running out of time, so I want to make sure I deliver this to you. Oh, by the way, here's something that's going to be up for you. Every day, I'm going to have a recommended prompt for tonight. Okay? This,
Wait, don't we need to do one?
right here, right in your